Okay, we will begin with Lecture 9, which is Chapter 11 on air masses and fronts. Basically, this chapter is divided up into two areas. The first one, we will talk about air masses. There are 5 air masses across North America. We'll identify those. And then we will use the definition of air masses and the classification of air masses to actually define fronts, such as cold fronts, warm fronts, stationary fronts, and we'll actually even touch on occluded fronts. The actual definition of an air mass is basically a very large body of air with similar temperature and moisture characteristics. And this takes place over a rather large area and at any given altitude. For example, in this particular map that you see here, it is a map of high pressure, and if you look at temperatures, the first thing that should jump out to you is that they are very cold temperatures, even down into the Gulf Coast states. You see temperatures in the teens. You also see dew points. Dew points in Iowa and portions of the Dakotas and Minnesota are extremely low. So this air is cold and dry, and so it has probably come down from Canada. And so this would be an example of a rather large air mass. In other words, a body of air having similar temperature and moisture characteristics. In this particular case, being cold and dry. Now, air masses basically will form above flat, uniform regions with light surface winds. Some of these areas would include Canada, the Arctic Circle, oceans such as the Pacific Ocean, the Gulf of Mexico, portions of Mexico, the Atlantic Ocean. These are areas that are flat, uniform regions with light surface winds. Basically, what you want to do is have the air sitting over a particular area long enough to where it takes on the same temperature characteristics and moisture characteristics of the surface underneath it. Once it does that, then we can classify it in terms of whether it's a moist air mass, which would be a maritime. When you think of maritime, you think of oceanic, or continental, which would be land. So in terms of humidity or moisture characteristics, we will look at maritime, which would be moist, continental, which would have a source over land, which would be considered dry. So for instance, if we look at maritime polar, that means that would be a cold air mass that comes in from the ocean. If we were to look at continental Arctic, this would be a cold air mass that came in from either, well, more than likely, the Arctic Circle. And then if we look at something called maritime tropical, that means a moist air mass that is warm. So we would describe this as a warm and moist air mass. So it's just a body of air that has characteristics of being warm and moist. Continental tropic would be characteristic of warm and dry. It's typically air originating over land masses, typically dry. And you see the different source regions. For instance, maritime polar typically is up over the northern Pacific, and so typically this air is cold, so it would be polar. And maritime, it's sitting over a body of water, so it's rather moist, so it would be cold, moist air that can move in from the North Pacific into the U.S. We also have maritime polar that sits up over the North Atlantic, and so that air is cold, but since it originates over the ocean, it's moist, and it can come into the U.S. from the northeast. We also have several places for maritime tropical. Maritime tropical being warm and moist. Maritime showing that it's originating over an ocean, tropical meaning it's warm. And so this typically comes in from the South Pacific into the southwestern states. For Iowa and the Gulf Coast states, maritime tropical air masses come in from the Gulf of Mexico. Maritime tropical air masses can come into the Atlantic states from the southeastern or southwestern Atlantic Ocean. Continental polar originates over Canada and comes down into the southern U.S. or into the U.S. Continental Arctic, typically up over Alaska. And since it's continental, it's over a landmass. Arctic, very cold. So this would be an example of very cold and dry air. Continental tropic. Continental tropical typically originates over Mexico or over Texas. Continental, meaning it's over land, is where this air originates. Tropical, meaning very hot. So this would be very hot and dry air. And so you may just take a few minutes here just to pause to look at the different source regions, and I'll go ahead and clear it all off here for you. And you can see the different air masses, how they're classified, and where they originate from. Just to give you an idea, over the last month, January and February, almost the last 2 months, we've had extremely cold, dry air. Our source region has been continental Arctic. This air has been coming out of Alaska, moving into Iowa. And in fact, that flow has been occurring over the last 2 months and has led to our very cold and somewhat dry pattern. Now, let's take a look at continental polar. Now, continental meaning it originates over a landmass, polar meaning very cold, and you see the air coming down as indicated by these arrows. High pressure. Typically, these air masses are associated with high pressure, and you look back on the 22nd of December, back in 1989, these are actual air temperatures. -30, -29, Minneapolis, St. Paul, -28, Kansas City, -23. Down in my neck of the woods in Louisiana, 5 degrees above zero. That's very cold air. Very rarely will this type of continental polar air mass make it into California because you have a mountain range here, the Sierra Nevadas, that tend to block the transport of continental polar air into the west coast, although sometimes it can leak over into that area. Now, what you're looking at here is a vertical profile, altitude being on the y-axis. This is surface all the way up to 6 kilometers. And then temperature being the x-axis. And what we're looking at here is how temperature changes with height. And a continental polar air mass doesn't happen very often in the summertime, but on occasions. In August, we may get cooler air, temperatures down in the 40s, coming down from Canada even in August. So it's possible to get this continental polar air coming in during the summer, and typically what we find is that temperatures are very warm at the surface, and as we go up into the atmosphere, temperatures begin to decrease, and this is a very unstable case. So we can often get thunderstorms that will form when we have these continental polar air masses coming down in the summer because of the warm air near the surface and the cold air sitting above the surface. Recall from, I believe it was Chapter 6 on stability, we talked about an unstable air mass being a very warm surface and colder air sitting up over the warm surface. Now, typically, we will see continental polar air coming in from Canada during the wintertime, where we'll see very cold surface temperatures, and right above the surface, temperatures begin to rise and begin to cool again as we go up. On a satellite feed, when you see continental polar air coming down, this is the Gulf Coast states. Here's Louisiana, Florida, and oftentimes we'll get this dry, cold air coming in and over the Gulf of Mexico. Now recall that the Gulf of Mexico, very moist air, and also warm compared to the air coming in off the land. And so we have warm surface air over the ocean, this cold continental polar air coming in, and so you have a very steep lapse rate. In other words, a very unstable atmosphere, and clouds will often form very quickly as this cold, dry air mass moves over the warm and relatively moist Gulf of Mexico. And so the cold air mass will actually see moisture being evaporated from the Gulf into the air, and so the air begins to move closer to saturation as we add more water vapor to this dry air mass. We'll see clouds forming. Same thing here. As air moves off the Carolina coast into the Gulf Stream, which is a very warm, moist current of ocean here called the Gulf Stream. Probably can't make that out, but this is the Gulf Stream, this area of warm oceanic air that is along the east coast of the U.S. Now, what will end up happening as this continental polar air moves in over the water, it will begin to warm, and so it will begin to modify. So it might move from continental polar to more of a maritime polar type of air mass. Let's talk about maritime polar. Again, maritime means the source region is water, polar meaning cold. This is the west coast of the U.S., Washington, Oregon, California. And so a lot of times you'll have low pressure sitting out here off the coast. We know winds are counterclockwise around low pressure. And so we begin to take this area of air that sits over the ocean that's cold. So it's maritime polar. And we begin to move it into the west coast of California, Oregon, and Washington. And oftentimes that will produce rain showers as we have moist air coming in off the ocean, moving in over land. Now what will happen a lot of times with this maritime polar air, it begins to get lifted over the Olympic Mountains, which are in western Washington. As the air begins to rise, it begins to cool, and it begins to rain, and so it begins to dry out. And so it begins to descend, and you recall from mountain sim, as air begins to descend down the mountain, it begins to warm by compression, moves further away from the saturation vapor pressure curve, and then begins to rise again as it hits the Cascade Mountains, which I believe is over in eastern Washington, and produces more precipitation that begins to go over the Cascades, begins to warm and dry out. And so now what we have, this maritime polar air, is now modified. It's become dry, and so now you have continental polar. Continental means it's basically dried out. It's now taking on more of the characteristics of the land, which is drier air, and so it begins to go up the Rockies. It begins to cool. It begins to, again, rain, and comes off the Rockies heading toward Iowa, and basically the air becomes very dry. So we've taken a very moist and cool air mass off the Pacific Ocean, running it over 3 different mountain chains, and by the time it hits Iowa, the air is rather dry and also not as cool as when it began out over the Pacific Ocean. And in fact, it may develop a Chinook wind, which is compressed air coming off the mountain, very warm air. So we take this originally cool, moist air, and we turn it into warmer, dry air by the time it hits Iowa. Also looking at maritime polar air, coming in off of the Atlantic, off of the North Atlantic. Anytime you have high pressure sitting over portions of Maine and eastern Canada, winds are clockwise around high pressure. And so we begin to bring this air mass that's sitting over the North Atlantic, which is cold and moist, and we begin to run it into the Atlantic states, the northeastern Atlantic states. And as we begin to bring this cold, unstable air in, we begin to produce rain over a portion of the eastern U.S. These types of storms are what we call nor'easters. Another type of air mass, if you look here, this is the western portion of the U.S. This is the coast of California. And you notice this streak of cloud cover. This is what we call maritime tropical air. Its source is the southeastern and southern Pacific Ocean, which we know is very warm and moist. And so we can bring this warm, moist air into the west coast of the U.S., even into the desert southwest. And since this air is very warm and very moist, it has a lot of energy and can produce a lot of storms in the western U.S. So there's a source of maritime tropical air which would produce storms over the western portion of the U.S. This is often referred to as the Pineapple Express, since the source region is back here over Hawaii. Another source of maritime tropical air is the Gulf of Mexico. And oftentimes when you have high pressure sitting out in the eastern portion of the U.S., we know that we have winds clockwise around high pressure, and so we begin to bring air in from the Gulf of Mexico. Air that's coming in from the Gulf of Mexico is often very warm and moist, and if it's associated with a cold front, a very slow-moving cold front, we can form a lot of storms in this particular area. In fact, these storms can last for many days and actually produce flash flooding. Notice that the low pressure center is sitting here over Iowa, and so we get air coming up, warm, moist air from the Gulf of Mexico, and we know that winds around low pressure are counterclockwise, and so we'll see east-southeast winds here in Iowa, warm, moist air, the air is being lifted around low pressure, and we can see quite a bit of stormy type weather. Another type of air mass, the continental tropical, occurs during the summertime. Oftentimes you'll have an area of high pressure sitting up over the southern U.S., and we know that winds or air out of high pressure begins to sink, it compresses, and as air compresses it begins to heat. And this air mass will sit for several days, and with clear skies will begin to warm quite a bit, producing very hot type dry air which can eventually move into Iowa. Okay, now that you have an understanding of air masses, let's move on and define fronts. Now, what we have here is fronts basically separate areas of differing air masses. For instance, we won't worry about what type of front this is that I'm outlining, but we have a line, some type of front, that's dividing maritime tropical, you see right here, maritime tropical air mass from continental polar air mass back here, and also dividing maritime polar air mass here. So this front, or series of fronts, divides three different air masses: maritime polar, continental polar, and maritime tropical. So basically fronts are zones of transition. In other words, down here along the Gulf Coast, we have warm, moist air. You see a temperature of 58, a dew point of 49. And then just a short distance across this front, we see temperatures of 23 and a dew point of 2, a temperature of 18, and a dew point temperature of 6. And then a few hundred miles to the south across this front, we see a temperature of 59 and a dew point of 50. So you definitely see a difference here between these fronts. So it's really easy just to think of fronts as just a transition zone between air masses. We see four different types of fronts here. You see the key here. This is a cold front, warm front, stationary. So from B to C here, we have a cold front. Notice that these, triangles is the best way to describe it, is pointing in this direction, which means the cold front is moving from northwest to southeast. We have a warm front here, and notice that the half circles are pointing in this direction, which means the warm front is moving from southwest to northeast. And then from point A to point B, we have alternating semicircles, triangles. This means a stationary front, which means the front is not moving. It's just sitting there stationary. Now, look at the low pressure center that we have here. We know that winds are typically counterclockwise around low pressure, and so winds are clockwise around high pressure, and so we see we're driving the cold air south into the Gulf Coast states. We also have an occluded front, which we really won't spend any time on, simply because we're not going to, that's more of an advanced topic. Let's talk about front identification. Basically, there are 4 things that we look for in drawing a front. And since we're dealing with differences of air masses, obviously temperature and moisture characteristics are items that we look at. And if we look at this cold front right here, we see that the cold front is moving from left to right because the triangles are pointing in this direction. And so we see temperatures in the 50s out ahead of this cold front, temperatures in the 20s and 30s behind this cold front. So we see a difference in temperature, dew points in the 50s out ahead of the cold front, dew points in the 20s and 30s behind the cold front. So again, drier air behind the cold front, more moist air ahead of the cold front. And so it's easy to see the differences between temperature and dew point between these air masses. We also look at wind direction. Let me clean some of this up here. Out ahead of the cold front, we see southeast winds, southerly wind, southeast, southeast, southeast. Behind the cold front, we see northwest, west, 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 northwest. So typically we see some sort of westerly component behind the front, some sort of southerly component out ahead of the front. So we would look at wind direction. We can also look at pressure. Typically behind a cold front, pressure begins to increase. Out ahead of a cold front, pressure begins to decrease. Recall from the module, I believe it was in Chapter 8, when we started talking about pressure and how we could look at barometric pressure to indicate whether fair weather or bad weather or poor weather was moving into an area. We can also look at cloud and precipitation patterns. I'll clean this up once again. But notice the green area is indicative of cloud and precip. And so near a cold front is where we tend to see these types of features. Now, what you're looking at here is if we took a slice of the atmosphere, we took a slice out of the side of the atmosphere, and we're looking, here's the cold front, and this cold front is moving from left to right. And so you see here this zone transition between the warm, moist air here to the right and the cooler, drier air here to the left. Now notice as the cold front is moving from left to right, air coming in from the east begins to rise up and over this cold dome of air. And in fact, the front, at the point where the cold front is at, the cold air goes up 1 kilometer and extends back 50 kilometers. So the cold air is not very deep in this particular example. In other words, it doesn't go up very high, but it's over a long distance, 50 kilometers or about 30 miles. So we're looking at 30 miles behind this front. And so as air begins to rise, notice again that the air is warm and moist, and it hits this area of cold, dense air. And this warm, less dense air begins to rise. And as it begins to rise, it cools, just like we saw in Mountain Sim. As air begins to rise, it cools and eventually cools to the condensation point. In other words, it hits the saturation vapor pressure curve. And if the right processes occur, we have the production of a cloud that produces rain, either a nimbostratus cloud, which gives us nice gentle rain, or a thunderstorm, which is what we see here, gives us very strong type precipitation. So again, this is a cross-section of a cold front. Notice that some distance out, again, this is where the cold front is at, but notice some distance out ahead of the cold front, notice that we begin to see cirrus clouds. Those are the thin, wispy clouds. As we begin to move to the left and we move closer to the front, the clouds begin to thicken into cirrostratus. That's what this CS is, cirrostratus. And then as we get right near the area of the cold front, they begin to lower and we have altocumulus clouds. And then right along the cold front and right behind it, we have a CB, which is a cumulonimbus, which is a thunderstorm. And then back behind the cold front, air begins to sink, skies begin to clear. Recall that sinking air warms and it moves away from the saturation vapor pressure curve, and so we begin to see clear skies. So there's a lot of information. You might want to spend some time looking at this particular slide to understand what's going on. Keep in mind, again, the cold front is moving from left to right. And typically, we can look for the strengthening of a cold front. We can look for that on the satellite imagery. Here you see a low pressure with a cold front back here. Notice there's not really a lot of clouds in this area along the front, but as this cold air begins to move out into the ocean, notice that we have warm, moist air here, and typically we have stronger storms firing as this cold front has moved out over into a different air mass. It begins to strengthen over warmer water, producing more precipitation. Another type of front, which we call a backdoor front. Now, this is interesting because typically most fronts move west to east or left to right. But in this particular case, if we have high pressure sitting off the coast of Maine, we have cold maritime polar air. Again, maritime means the source region is out over water. Polar means it's cold. We can bring in cold air, a cold front, coming in from Canada, moving to the southwest. Now, this does not happen very often, but it can happen on occasions. And you see the difference in temperature across that front. 75 in Pennsylvania, it looks like that's probably near Philadelphia. And then over in Boston, a short distance, it's 45. So again, we have this type of cold front that can move down from Canada. Typically, this does not occur very often. Another type of front, a warm front, and again, this is moving in this direction, the direction the semicircles are pointing. And notice out ahead of this warm front, we have cool temperatures in the 30s. Behind the warm front, we have temperatures in the 40s and 50s. So again, and notice the dew point, 50, dew point 46, dew point 49. Moist air compared to the region out ahead of this warm front, where dew points are in the low 30s, even in the 20s. So we have cool, moist air here. So this would probably be maritime polar. Warm, moist air here, which more than likely would be maritime tropical. And so right where this front is at is the dividing line between these air masses. And as we would expect, as this front continues to move north, these temperatures should begin to rise. So we have warm, less dense air sitting behind the warm front. We have cooler, more dense air out ahead of the warm front. So what ends up happening, this warm air hits the cold air and begins to rise. And as the air begins to rise, it begins to cool, eventually condenses, producing precipitation. In fact, if we take a cross-section of the atmosphere, just like we did with the cold front, this is the warm front right here. It's moving from left to right. Notice that we have cool air out ahead of the warm front, warm air back behind the warm front, and notice that this warm air is riding up and over the cooler, more dense air. And so the air begins to rise. And typically right ahead of the warm front, you'll see stratus clouds. Those are the low clouds. And as the air continues to rise and cool, we begin to produce a gentle rain or snow with a nimbostratus cloud. And then as we begin to move further away from the warm front, the clouds begin to thin out into altostratus, cirrostratus, and cirrus. So if you're sitting out here and you see cirrus clouds, and you see it going into cirrostratus, altostratus, and nimbostratus, then you probably have a warm front moving into your area. An occluded front basically is when cold air catches up to, for instance, in this particular case, very cold air, a strong cold front. You have cool air or cold air sitting here and a warm front in between, or warm air in between these two air masses. This very fast moving air, cold air, will catch up with this colder air and lift the warm air up over it. This is what we would call a cold air occlusion. We typically won't worry about these too much. We won't concern ourselves because, like I said, this is something we won't see very often. And here you see a mid-latitude cyclone with an occluded front, a cold front, and a warm front. And you see the signature of that low pressure system in the satellite imagery. These storms typically show up quite a bit as far as mid-latitude cyclone storms in our area.